Okay, this is section 14.4, buoyant forces and Archimedes principle. I'm sure you've uh, taken some kind of ball, beach ball or something like that and tried to push it underwater. We used to, it was always a challenge between my cousin and myself to try to push it down and see if we could sit on it. Most of the time we weren't successful because it's real hard to push a ball down. Um, in water because of the buoyant force. The buoyant force B on a beach ball that replaces this parcel of water is exactly the same as the buoyant force on the parcel. So the buoyant force, the if you take this parcel of water that is equivalent, um, the buoyant force is equal to the force of gravity of this amount of water. Well, since this amount of water is the mass is so much greater than the empty beach ball, the force is upward. That's the buoyant force. So that's why it's so difficult to push an inflated ball down uh, underwater. So the magnitude of the buoyant force on an object always equals the weight of the fluid displaced by the object. Uh, so the buoyant force um, on the cube is the resultant of the forces exerted on its top and bottom faces of the liquid. So here uh, on the top surface, you have the buoyant force and uh, the force of gravity from this uh, item down here at the bottom. So the buoyant force is equal to the pressure at the bottom minus the pressure at the top times the area. So it's the density of the fluid times GH, where H is the height of the object, times the area. So it's the buoyant force is the density of fluid times G times the volume. Uh, so it's the uh, mass of the fluid times G, in which the density uh, times the volume is the mass of the fluid times the gravitational force. Now, fish are um, actually weigh a little bit more than the density of water, and they have an air bladder that they adjust to allow them to swim to different depths. Um, so you can have like uh, if an object is totally submerged, then the density of the object is greater than the density of the fluid. And if it floats, you have uh, the density of the object is less than the density of the fluid. Like a block of wood or even ice. We learned earlier that, or no, maybe we haven't gotten there yet. That we'll see that ice is less dense than water, and so it floats. There's a certain part of the ice, even you talk about an iceberg. That is, I forget what it is. 10% of it or so is above the water. The rest of it is below the water. Um, so the force of gravity is equal to mg is equal to the density of the object times g times the volume of the object. So the buoyant force minus the gravitational force is equal to the density of the fluid minus the uh, density of the object times g times the volume of the object. Um, so with a floating object, uh, the density of the object is less than the fluid because the object floats in equilibrium. B is equal to the buoyant force is equal to the force of gravity. So B is equal to the density of the fluid times G times the volume displaced. The force of gravity is equal to mg, which is equal to the density of the fluid times G times the volume of the object. And the buoyant force, F of G, is equal to the buoyant force, which gives you that the density of the fluid times G times the volume displaced is equal to the density of the fluid times G times the volume of the object. So the volume displaced divided by the volume of the object is equal to the density of the object uh, divided by the density of the fluid. So you can see the object and the density of the object, the volume of the object and the density of the object are in opposite sides of the equation. Okay, you're shipwrecked and floating in the middle of the ocean on a raft. Your cargo on the raft includes a treasure chest full of gold that you found before your ship sank, and the raft is just barely afloat. To keep you floating as high as possible in the water, what should you do? Assume throwing the treasure chest overboard. Uh, Assume throwing the treasure chest overboard is not an option you wish to consider. Leave the treasure chest on the top of the raft. Secure the treasure chest to the underside of the raft. Um, Hang the treasure chest in the water with a rope attached to the raft. Well, either of these last two will do it. Uh, so, um, and that's it for this. Uh, Let's see if there's a. In all three cases, the weight of the treasure chest causes a downward force on the raft that makes the raft sink into the water. In B and C, however, the treasure chest also displaces water, which provides a buoyant force on the upward direction, reducing the downward force on the raft. So the raft will sit higher in the water if you secure the treasure chest to the underside of the raft or hang the treasure chest in the water with a rope attached to the raft. All right. And next we'll go to fluid dynamics.